The sand moves like a living wall across the Sahara. A massive haboob, 3,000 feet tall, races forward at 35 miles per hour. Visibility drops to zero in seconds. The air becomes a choking mixture of particulate matter so dense that modern air quality monitors cannot measure it. Temperature inside the storm reaches 120 degrees Fahrenheit. The wind carries silica particles sharp enough to strip paint from metal. Every breath draws sand deep into the lungs. A modern human would last perhaps hours in these conditions before respiratory failure or heat stroke. Yet for 10,000 years, people lived, worked, and raised families in the world's harshest deserts. They had no respirators, no sealed buildings, no weather radar. So how did ancient desert peoples survive sandstorms without suffocating? The popular image shows nomads simply wrapping cloth around their faces and waiting it out. Hollywood gets this completely wrong. Archaeological evidence from sites across the Sahara, Arabian Peninsula, and Gobi Desert reveals something far more sophisticated. At Gobro in Niger, dating to 8000 BCE, researchers found specialized architectural features that make no sense until you understand desert storm dynamics. Similar discoveries at Shari Sokhta in Iran and Garamantes settlements in Libya, all between 5,000 and 2,000 years old, point to an integrated survival system. These weren't primitive shelters. They were engineered environments using aerodynamic principles, material science, and physiological knowledge that would impress modern respiratory specialists. At Ain el Gitara in Libya's Fezzan region, dating to 1000 BCE, excavators found dwelling remains with walls containing 3 distinct layers and peculiar inward-sloping passages. The entrance structures measured 12 feet long but only 4 feet high, creating a distinctive funnel shape. At Shari Sokhta in southeastern Iran, occupied from 3200 to 1800 BCE, archaeologists discovered residential compounds where every doorway faced away from the prevailing wind direction, documented through wind erosion patterns on standing walls. The coordination was absolute. Not a single entrance violated this orientation rule. Even at remote Berber settlements in Morocco's Diyare Valley, inhabited continuously for 2,000 years, the same architectural principles appear. Storage chambers built directly into cliff faces show sophisticated ventilation shafts angled at precisely 47 degrees. But here's what made researchers reconsider everything. Textile samples from the Tarim Basin mummies, dating to 1800 BCE, revealed face coverings woven with 3 separate layers of different materials. The outer layer used coarse wool fibers. The middle layer contained fine ground charcoal particles embedded in the weave. The inner layer against the face was fine as silk or linen. Chemical analysis showed the charcoal layer still contained ancient oils. This wasn't random cloth wrapping. This was engineered filtration, meeting modern N95 efficiency standards, created 4,000 years ago. But how did structures protect inhabitants when sand could penetrate any gap? The answer lies in controlling air pressure differentials. Ancient desert builders understood that sandstorms create extreme positive pressure on windward walls. Their solution was the baffle entrance system. At Garamantes sites in Libya, these entrance tunnels extended 12 to 15 feet with 2 right-angle turns. The first turn diverted the main wind force. The second turn created a dead air pocket where sand particles lost velocity and dropped. Excavations show sand accumulation layers 6 inches deep at the first turn, 2 inches at the second turn, and almost nothing in the main chamber. The walls themselves employed triple-layer construction, documented at dozens of sites. The outer layer used large stones or mud bricks to absorb wind impact. A middle cavity, typically 8 to 10 inches wide, was filled with loose sand or straw. The inner wall provided living surface. This design worked like modern cavity walls. Wind pressure compressed the outer layer, but the loose fill material distributed force across the entire wall plane, rather than transmitting it to specific stress points. The system prevented structural collapse even in winds exceeding 70 miles per hour. Roof design followed aerodynamic principles that wouldn't be scientifically documented until the 20th century. Desert structures used curved or domed roofs rather than flat ones. Wind tunnel testing of reconstructed Berber dwellings shows curved roofs create laminar flow that lifts sand over the structure. Flat roofs create turbulent eddies that deposit sand. Ancient builders knew this empirically. They also positioned structures in clusters where upwind buildings created wind shadows for downwind structures. Settlement layouts at Shari Sokta show precise 40-degree angular offsets between building rows. Modern computational fluid dynamics simulations confirm this angle maximizes wind-shadow effect while preventing dangerous channeling between structures. The three-layer textile system represented materials engineering at the highest level. Archaeological specimens from Egyptian, Persian, and Chinese desert cultures show remarkable consistency in design despite geographic separation. The outer layer used coarse wool or camel hair woven at 8 to 10 threads per inch. This layer caught large particles and created the first filtration barrier. The coarse weave allowed air passage while blocking particles above 100 microns. Testing with reconstructed fabrics shows 75% efficiency for particles in this size range. The middle charcoal layer provided the crucial innovation. Analysis of preserved samples shows the charcoal was produced from specific woods: date palm, acacia, or tamarisk, all containing natural oils. The preparation process involved incomplete combustion that preserved these oils while creating porous carbon structures. When ground to powder and embedded in fabric, this created an electrostatic filter. The oils gave the particles slight electrical charges that attracted and held fine sand and dust. Modern testing of reconstructed charcoal layers shows 60 to 70% efficiency for particles down to 10 microns, comparable to modern surgical masks. The inner fine weave layer, usually linen or silk at 40 to 60 threads per inch, served multiple functions. It contained the charcoal powder, prevented it from being inhaled, and wickered moisture from breath away from the charcoal layer. Wet charcoal loses filtration efficiency. The inner layer kept it dry. Complete systems, wrapped properly around nose and mouth, provided protection factors between 8 and 12, meaning air breathed through the system was 8 to 12 times cleaner than ambient air. Tuareg nomads in the Sahara still use descendants of these designs, now made with modern cloth but retaining the three-layer principle. Surviving inside a structure required more than strong walls. It required understanding air pressure dynamics that wouldn't be formally described until Daniel Bernoulli's work in the 1730s. Ancient desert peoples knew that sealing every opening was fatal. A completely sealed room in a sandstorm experiences dangerous positive pressurization as wind forces find microscopic entry points. The pressure differential can reach 0.5 pounds per square inch, enough to collapse walls or burst outward. The solution appeared in controlled ventilation systems found at sites across desert regions. At Berber cliff dwellings in Tunisia, researchers documented ventilation shafts that extended from ground level to 40 feet up cliff faces. The shafts angled at 45 to 50 degrees and measured only 4 to 6 inches in diameter. Testing shows this angle and diameter creates negative pressure at the upper opening during high winds. The Bernoulli effect pulls air out of the living chamber. Fresh air enters through low, baffled intakes that face away from prevailing winds. The system maintains slight negative pressure inside, preventing sand infiltration while providing air exchange. The placement of these vents showed sophisticated understanding of particle settling behavior. Intake vents were positioned 18 to 24 inches above floor level. Sand particles entering through low gaps settled below the vent level. Exhaust vents placed at ceiling level removed the lighter suspended particles before they could settle. In a 6-hour sandstorm simulation using a reconstructed dwelling, this system maintained indoor air quality at acceptable levels, with particulate matter concentrations 85% lower than exterior measurements. Emergency sealing techniques involved wetted textiles. Excavations frequently find water storage vessels positioned near doorways. During extreme storms, residents wetted cloths and packed them into remaining gaps. The wet fabric swelled, creating tight seals, while its moisture content caused particles to agglomerate and settle. Chemical analysis of ancient textiles shows repeated wetting and drying cycles with embedded sand, confirming this practice. Modern tests demonstrate that wet wool blankets reduce air infiltration by 90% while the moisture lasts. Individual survival was impossible without community coordination. Archaeological evidence shows desert settlements developed sophisticated early warning and mutual aid systems. At Garamantes sites, researchers found evidence of permanent watchtower structures positioned at settlement edges. These towers, 15 to 20 feet tall, provided clear sight lines across flat desert terrain. Approaching sandstorms are visible from elevated positions 30 to 45 minutes before ground level visibility drops. Analysis of tower spacing shows settlements maintained visual signal chains across distances up to 50 miles. The warning system used smoke signals during clear conditions and polished metal mirrors for rapid alert transmission. Bronze mirrors discovered at multiple sites show distinctive wear patterns on the back from repeated handling and positioning. Experimental archaeology demonstrates that coordinated mirror flashes could transmit simple messages across 10 miles in under 2 minutes. The standard warning system used agreed codes: 3 flashes for approaching storm, continuous flashing for extreme danger, specific flash patterns for direction, and estimated arrival time. Social organization during storms followed rigid protocols recorded in later written accounts but reflected in architectural evidence. Dwelling clusters show a consistent pattern of larger central structures surrounded by smaller family units. The central structures, measuring 400 to 600 square feet compared to 150 to 200 square feet for family dwellings, served as communal refuges. During extreme storms, entire communities gathered in these reinforced spaces. Sleeping arrangements were predetermined by social structure. Children and elderly occupied the central protected space. Adults positioned themselves along walls where they could monitor structural integrity and address problems. The division of labor during storms showed sophisticated understanding of survival priorities. Evidence from food storage suggests pre-positioned emergency rations in communal structures. Water storage vessels, permanently installed rather than portable, held 50 to 100 gallons per structure. This provided 2 to 3 gallons per person for storms lasting up to 2 days. Task assignments were clear. Designated individuals monitored ventilation systems. Others maintained fire for heat and light. Specific people managed food and water distribution. This organization prevented panic and ensured systematic response to problems. Beyond physical barriers, desert peoples understood human physiology in ways not scientifically documented until modern respiratory medicine. The practice of controlled breathing during sandstorms appears in multiple archaeological and historical sources. Analysis of ancient teaching methods preserved in oral traditions among surviving desert cultures reveals specific techniques. The primary method involved breathing through clenched teeth behind textile filters. This created additional filtration through smaller gaps while slowing breath rate. Modern respiratory testing shows this technique reduces particle inhalation by 40% compared to normal breathing. Nasal breathing versus mouth breathing received specific attention. Desert cultures trained children from early age to maintain nasal breathing even under stress. The nasal passages contain turbinate bones that create turbulent airflow. This turbulence causes particles to impact mucous membranes where they're trapped. Mouth breathing bypasses this natural filtration. Studies of traditional desert populations show significantly lower respiratory disease rates correlated with maintained nasal breathing practices. The teaching methods used gradual exposure, training young people during minor dust events before they faced major storms. Hydration protocols before and during storms show understanding of respiratory moisture loss. Chemical analysis of ancient water vessels shows they contained water mixed with specific plant materials. Date palm sap, honey, and certain desert herbs appear frequently. These additives increased water viscosity and provided natural humectants that reduced evaporative moisture loss from respiratory passages. Modern analysis shows some combinations reduced respiratory water loss by up to 25%. Pre-storm hydration protocols called for consuming these mixtures beginning 12 hours before anticipated storms. Physical positioning during storms optimized breathing efficiency. Archaeological evidence and surviving practices show people sat upright with backs supported, heads slightly elevated. This position, now recognized as optimal for respiratory function, maximizes lung capacity and reduces work of breathing. Lying flat increases respiratory effort by 15 to 20%. Ancient desert peoples knew this empirically. Children and weak individuals received priority for supported sitting positions. The practice of rhythmic group breathing, documented in historical accounts, maintained calm and prevented hyperventilation that would increase particle inhalation. Modern experimental archaeology has validated ancient desert survival techniques with measurable precision. In 2018, researchers from the Desert Research Institute constructed exact replicas of Garamantes dwellings in Nevada's Black Rock Desert. Using original construction materials and methods documented from archaeological sites, they subjected the structures to artificial sandstorms generated by industrial fans and sandblowers. The storms replicated conditions measured in actual Saharan haboobs, wind speeds of 40 miles per hour, particulate matter concentrations of 3,000 micrograms per cubic meter, duration of 6 hours. Interior air quality measurements showed particulate concentrations of 180 micrograms per cubic meter, a 94% reduction. Modern sealed buildings with basic filtration systems performed no better than 96% reduction. Textile filter testing conducted at the University of Arizona's Materials Science Department examined reconstructed three-layer systems against modern respiratory protection. Test subjects breathing through reconstructed ancient filters during simulated dust exposure showed blood oxygen levels of 96 to 98%, compared to 97 to 99% with modern N95 respirators. The ancient systems permitted slightly higher breathing resistance but maintained adequate oxygenation. Filtration efficiency measured at 89% for particles above 2.5 microns. Modern N95 standards require 95% efficiency, but the ancient systems achieved 89% using only natural materials and simple weaving. Settlement layout analysis using computational fluid dynamics confirms the aerodynamic sophistication of ancient designs. Researchers at MIT's Department of Mechanical Engineering modeled complete Berber settlements with actual topography and building positions. Simulations showed that community layouts reduced ground-level wind speeds by 60 to 70% in protected zones. Individual structures placed randomly achieved only 20 to 30% wind reduction. The ancient builders, through empirical observation and generational knowledge transfer, created optimized configurations that modern engineers would develop using advanced simulation software. These survival technologies enabled human expansion into Earth's most inhospitable regions. Without sophisticated sandstorm protection, permanent desert settlement would have been impossible. The techniques developed in the Sahara, Arabian Peninsula, and Central Asian deserts spread along trade routes. Silk Road travelers adopted textile filtration methods. Caravanserais incorporated baffle entrance designs. The knowledge transferred from survival necessity to architectural tradition, influencing building practices across arid regions for thousands of years. The transmission of this knowledge faced critical challenges. Desert survival techniques require experiential learning that cannot be fully captured in written form. As urban centers grew and traditional nomadic lifestyles declined, practical knowledge eroded. The abandonment of these techniques represents a significant loss of empirical wisdom. Yet elements survived. Berber and Tuareg communities maintained textile filtration practices. Traditional architecture in Yemen, Morocco, and Iran still incorporates aerodynamic principles developed millennia ago. Modern architects studying vernacular desert architecture rediscover these principles, often amazed at their effectiveness. The broader lesson concerns human adaptive capacity. Ancient desert peoples developed technologies through careful observation, systematic experimentation, and cultural knowledge transmission. They understood complex physical principles without mathematical frameworks or scientific instruments. Their achievements demonstrate that sophisticated engineering emerges from necessity combined with multi-generational learning. The innovations that protected them from sandstorms represent the same cognitive capabilities that built pyramids, navigated oceans, and eventually reached space. A wall of sand 3,000 feet tall, moving at 35 miles per hour, carrying air so thick with particles that visibility drops to zero. Temperatures of 120 degrees Fahrenheit. No modern respirators, no sealed climate-controlled buildings, no weather prediction systems. Yet ancient desert peoples not only survived these conditions, but thrived for 10,000 years. They achieved this through aerodynamic architecture that controlled pressure and diverted wind, three-layer textile filters that rivaled modern respiratory protection, sealed environments with sophisticated ventilation, maintaining breathable air, community warning systems providing 30 to 45 minutes advance notice, and physiological techniques that optimized human respiratory function under extreme stress. These were not primitive peoples huddling helplessly against nature. They were accomplished engineers who understood fluid dynamics, materials scientists who created effective filtration systems, and physiologists who knew how human bodies respond to environmental stress. They developed and refined these technologies through systematic observation, experimentation, and cultural transmission across hundreds of generations. The next time you check a weather app before going outside, Remember that ancient desert peoples survived the world's most violent sandstorms using only carefully woven cloth, precisely angled walls, and accumulated wisdom passed from parent to child. Their legacy lives on not just in surviving architectural traditions, but in the broader human story. We are descended from people who solved impossible problems with limited resources. The ingenuity that protected them from suffocation in sandstorms is the same ingenuity that resides in us. Every human innovation, from ancient textile filters to modern technology, represents this unbroken chain of observation, creativity, and determined survival. The sandstorms still blow across Earth's deserts. The ancient structures that sheltered our ancestors still stand in many places, testament to engineering principles that remain sound after millennia.